Hi, my name is Pepe Eulzer, and I will give you a short introduction to the HAExplorer, which is a system we developed for the analysis of biomechanical motion data. Biomechanical research aims to derive a better comprehension of the musculoskeletal system, which makes it possible to understand injury mechanisms, implications of diseases, and determine the quality of motion. In the common research process, we try to analyze a certain motion that was captured or simulated by deriving parameters that characterize the kinematics and may be helpful to better understand the effects of a motion. These biomechanical models are used in personalized medicine, for example, to develop better implants, but they are also crucial for the design of safety equipment and interaction devices. One of these parameters is the helical axis of motion. This is a precise 3D vector that a body rotates about and translates along during motion. The helical axis yields consistent kinematic information, can be reliably measured, and can be derived from all sorts of experiments, in vitro, in vivo, also motion simulations. A drawback of the helical axis is that it is sometimes too precise, so it creates a multidimensional and time-dependent data that is hard to analyze. And to address this issue, we developed the HAExplorer, which is a toolbox for helical axis analysis. It takes as input a sequence of marker positions or rigid transformations that describe the motion of different objects in a scene and then allows you to compute, filter, and compare the helical axis of motion of these objects. Once a dataset is loaded, a helical axis set can be created for any individual object. This is as simple as selecting at FHA World and then choosing any object in the scene. The helical axis is automatically computed for every time step in your data. We use an arrow glyph to display the location and orientation of the axis for every time iteration. You can replay an animation of the motion, during which you will see how the helical axis of the selected body changes over time. In each time step, the body rotates around the displayed arrow, following the right-hand rule. This is nicely visible here. When the spine flexes forward, the arrow glyphs point to the right, and when it turns around, the axis point into the opposite direction. The time window of visible glyphs can be easily resized or shifted, which allows to select and view a specific sequence in the whole motion. We can also modify how the glyphs appear in the world and pull them apart on their axis to make the scene clearer. The helical axis over time changes position, and as you can see, it traces a surface, which can also be visualized if needed. So you can see the continuity a little bit better. The color that you see in the glyphs and on the surface is a gradient that is mapped to the total time range of the motion. You might have noticed that is also shown here on the time slider. And this mapping helps to identify what happens when in the scene, even if you're just looking at this static representation. If you need to replay a specific sequence of the motion but don't want to change the time window, we also got you covered. So selecting live view right below the play button gives you the ability to hover over the timeline and control the active time this way. You see the highlighted glyph is the helical axis that describes the motion at its current point. This gives you really granular control over the temporal dimension. On the right, you'll find a scatter plot and two line plots, which show the quantitative components of the helical axis, that is, the amount of rotation and translation that happens at any given point in time, or more specific, the rotation and translation velocity. The scatter plot shows the correlation between these two quantities. So we just map the location of every discrete data point, and the line plots show the rotation velocity and translation velocity over time. And they give a really precise impression of the numerical values and clusters or components of the motion. The scatter plot also doubles as a tool to filter the attributes. We integrated this region of interest widget where you can select a data range that should be shown in the 3D view. This way you can filter out all axes with, for example, rotational velocity close to 0, so if almost no rotation occurs. And sometimes this can give you a much clearer view of the scene, and you can already tell apart clusters that appear to be the principal rotation axis of this motion. Now, for comparing objects, you can add as many helical axis sets as you need, and each will get its own color in the scene and in the graphs, which also shows up around the selected object, so you can tell the sets apart. And you can also turn the sets on or off. We conducted 2 user studies on the HAExplorer. The first with our close collaborators, where we did a 2-week diary study to see how they would use the tool in their daily work. And we also recorded their interactions when they were analyzing the real data they were working with, and we found that they often switched between spatial interaction and time or attribute filtering, which indicates an explorative workflow. In the second study, we gathered impressions from 6 biomechanics experts that are not part of our lab or the project, and we found that the HAExplorer was very positively received, especially regarding the interactiveness of the tool, which allows to experiment with the data without the cumbersome process of creating helical axis parameters manually. The HAExplorer is the first visualization system that is designed to support HA analysis on arbitrary models and motion sequences from any biomechanical experiment. The user feedback suggests that interactive exploration, as it is integrated in the HAExplorer, is a valuable asset for kinematic data analysis, and that contextualization with 3D models and animation can provide an intuitive framing to these live experiments. And ultimately, these may enable new insights into complex and interdependent motions.